Let's remember.
Okay, 9-6. So this section is on solving exponential equations, and then we're also going to solve some logarithmic equations. Okay, so you're going to decide what kind of method you're going to need to use based on the information that's given to you. If you're solving an exponential equation, which means an equation where the x that you're trying to isolate is in the exponent, the first thing you're going to see is whether or not you can change or make both sides of the equal sign have the same base. Okay, like if you're looking at problem like number 1, so we're solving for this x in the exponent. If I can change the other side of the equation to have the same base or be base 3 like this side, then that's what I want to do. So let's see if we can rewrite 243 as a base of 3. So let's see, 3 to the first power is 3, 3 squared is 9, 3 to the third power is 27, 3 to the fourth. So if I do 27 times 3 again, it's 81. So I'm either going to get 243 or I'm going to pass it at some point. So let's see, 3 to the fifth power. So now if I do the 81 times 3 again, it does give me 243. Okay, so if I can change the other side to have the same base as this side, then that's what I want to do. So now I have 3 to the x power. I can change this 243 and rewrite it as 3 to the fifth power, right? Because these are the same thing. I haven't changed anything. So now, if you can make your bases equal, then you're just going to set the equation as making the exponents equal to each other. And once you do that on this one's already solved. Because 3 to the fifth power is 243. Okay, so another example that's like this. So you have 4 to the 4x power equals 64. So again, I'm going to try to do the same thing. I'm going to try to rewrite this right side with a base of 4. So let's see, 4 to the first is 4. 4 squared is 16. 4 to the third power does give me 64. So I'm going to rewrite 64 as 4 to the third power. So now that your bases are the same, you'll set your exponents as your equation. So I need to make 4x equal to 3. And this one I do have another step, right? To get the x by itself, I just need to divide both sides by that 4. So x equals 3/4. But what if this is not the case, right? You're not always going to be able to rewrite the other side so that they have the same bases, right? So let's look at what we're going to do in that situation. So say you have 2 to the x power equals 19. So you're not going to be able to write 19 with the base of 2, right? You're going to pass over it, right? If you do the 2's, 2 squared is 4, 2 to the third power is 8, 2 the 4th is 16, but then 2 to the 5th is 32. So you're skipping over 19. So we can't use that method. Now, remember on our last section when we did all those properties of logarithms. Remember the property that shows if your logarithm has an exponent, you can rewrite it, right? By doing what? Where does this exponent come? Down here, right? So this can be rewritten as 5 times log base 10 of x. So I'm going to use that property, logging both sides. That's what's going to bring the x out of the exponent, right? Now, I can do it as long as I have to do it to both sides, right? I can do anything I want to an equation as long as I do it to both sides. So I'm going to use this property here and log both sides. Because I can't isolate the x while it's up in the exponent. That's what's going to bring it down. So now this left side can be rewritten as x times log 2 equals log 19. So now I can isolate this because this says x times log 2. So I need to get rid of this, which means I need to do what? That's right. Log 2, divide by it on both sides. That cancels it. There's your x all by itself. And then that's calculator work, right? So in your calculator, you'll just type in log 19, close the parenthesis after the 19, divided by log 2. So just log 19 over log 2, hit enter. It's going to give you a long decimal that you'll round to 4 spaces. So let's see, that'll give me 4.2479. Now remember, when we're rounding to 4 spaces, we always want to see the 5th spot. So since that's a 2, that just means I don't need to round up the 9, right? So I can leave it just like that. So again, you're going to, first of all, see if you can simplify the right side to have a base of 2. If not, to be able to get the x out of the exponent, you're going to have to log both sides. All right, what about this one? 2 to the 6x minus 1 equals 16. Right, I left this up here. Can you rewrite 16 with a base of 2? Yeah. So you want to use, that's the easier method, right? You want to use that method anytime you can. So I'm going to rewrite the right side as 2 to the 4th power. So if you can make your bases the same, then just set up the equation with the exponents. So 6x minus 1 equals 4. And then solve it for the x. So add the 1 to both sides. So 6x equals 5 and divide by 6. So x equals 5, 6. All right, so Fabian's asking, how did 2 to the 4th equal? So this, like this one right here. So this 2 to the 4th is the same amount as 16. okay? Because 2, if I multiply 2 together 4 times, it does give me 16. So my goal was to make this 16 have the same base as the other side. So if I can rewrite this 16 as 2 to a power to make the bases on both sides equal. Okay, now let's look at this one. Another one where you can't do both sides to make them have the same base. So you have 2 to the x power equals 6. Okay, so I cannot, look, if I'm doing a base of 2, it skips over 6, right? So because it goes from 4 to 8. So I cannot rewrite 6 as 2 to a certain power easily. Okay, so that means what method am I using? How am I going to get that exponent down? You're going to log both sides. So log of 2 to the x equals log 6. And then rewrite that left side, bringing the x out of the exponent. So x log 2 equals log 6, and then getting this x by itself. Divide both sides by log 2. So there's your x isolated. In your calculator, you'll do log 6 divided by log 2. And round it to 4 places. So this time I have 2.5849. So I want to go one more spot. That next spot is a 6, which means what's happening? What's this going to turn into? 50. Good. So you have 2.5850, since that 6 rounded it up. All right, this next one, we're going to run into something that we haven't seen yet. 10 to the negative x equals 2 to the 6x. Okay, so I can't rewrite the 10 with a base of 2. So I am going to have to use the log method to get those x's down. Okay, what's different is they both have x's in their exponents, but logging both sides is just going to be able to bring them both down, right? So I'll have log 10 to the negative x equals log 2 to the 6x, but then just rewrite both sides, bringing those x's out. So now here I have negative x log 10 equals 6x log 2. Now, what we haven't seen before, so your goal is to get the x by itself, right? But what do I have? I have x's in 2 separate areas, and those aren't like terms. It's not like I can just put those x's together. They're not like terms, okay? If you have this situation, you do want all the x's on the same side as each other. So let's move this whole term over here. So if I'm going to get rid of it here, I just need to add the x log 10 to both sides. So it cancels it on the left. Now, again, these aren't like terms, so I can't put them together. So I'm just going to write this whole thing out over here. So 6x log 2 plus x log 10. Now, the reason you want both of your terms that have x's on the same side is because now, what do these two terms have in common? The x, which means it's the greatest common factor and I can pull it out. Which then, what will I show? I'll still have my x's, but they'll just show as that one x, right? If I took the x out of each of these terms, put in parentheses what's left after you take the x out of those. So if I take the x out of this first term, I'm just left with 6 log 2 plus. If I take the x out here, I'm left with log 10. Now, this is the x I'm trying to get by itself, so I would have to divide both sides by this whole thing here. 6 log 2 plus log 10. But look at the other side. When I look at this other side, right, it canceled on the right. So there's my x by itself. Look at what your numerator is. What is 0? Doesn't even matter what the denominator is, right? Because 0 over anything is still just going to be what? 0, right? The undefined is if the zero's right in the bottom. Now, this next problem, remember when we first started talking about logs and how all the different bases that logs can have. One of those bases was an e. This can, remember how what this was. This could also be rewritten as ln, the natural log, right? That's what log base e is the same thing as. So let's remember that when you're looking at a problem that has an e, like number 7, you have e to the t power equals 629. So the t that you're solving for is in the exponent, just like the other ones. So I need to bring it down. So instead of logging both sides, I'm actually going to use the ln on both sides because I'm dealing with the e, and you'll see why on this next step. Because the ln has the same properties as the logs. I can still use the property where I can rewrite this side with the t brought down. So now I have t times ln e equals ln 629. Anytime you see this, that is actually just equal to 1, because remember, when you're finding logarithms, what are you doing? You're saying, what power do I need to raise this base to in order for it to equal what's in this position? So what would I have to raise 10 to in order for it to be 10? 1. Remember when we worked those problems, those long problems, where you changed that part to 1 if these two things were the same? So that's what's happening here. Because what is ln? Log base e. So if I have log base e of e, then this right here, that's really just 1. So I have t times 1, which is just t. So So all I need to do in my calculator is put in the ln 629. And remember where your ln button, right? It's right under that log button. So 6.44413. So the 3 tells me I don't need to round it up. All right, try this one. E to the negative 0.015t. Equals equals 0.43. So try that one by ln'ing both sides to bring down that exponent. Oh, baby, yes, if there, you're right. That is safe to say. If there is an x in the exponent on both sides, and those are the only terms on both sides, it is going to be 0, because once you bring those x's down and then put them on the same side as each other, there's not going to be anything left on the other side. So yeah, you're right. That is very safe to say. It's really just going to be times 1. So I just have over here negative 0.15t equals ln of 0.43. So if I'm solving for t, I just need to divide by what's hooked onto it. So negative 0.15 on both sides. So there's your t by itself, and then this is calculator work. So let's see, I've got ln 0.43 divided by negative 0.15, which gives me 5.6264. The next number is 6, which means you'll round the 4 up to a 5. So 5.6265. All right, what about this? 15 to the x equals 5 to the x plus 2. So, baby, on that last one where you said, is it safe to assume if there's x's in both the exponents that the answer is going to be 0? Yes, unless the x is, there's more than one term in the exponent. Because when I'm going to have to log both sides, right? Because I can't turn 15 into a base of 5. So when I log both sides, to bring the exponents down, on the left side, I just have that one term in the exponent. So I'm just going to bring the x down. But over here, I bring down both of those, x plus 2 log 5. So this x and the 2, I'm going to distribute over there now, which is why this one's not going to end up being 0, because if I distribute this, one of the terms is not going to have an x in it, right? Because if I distribute over here, x times log 5, plus, when I distribute this 2, I have 2 log 5. On the left, I have x log 15. So when I did this side, it did give me a term that doesn't have an x in it. So that's why this one is going to be different than that last one, okay? But I do want to have the terms that have the x's in them on the same side, because I'm going to use that same rule. If I put my x's on the same side, then I'm going to pull that x out. Okay, so I'm going to move this x term over here with this one. So I'm going to subtract x log 5 from both sides. So that cancels it over there. On the left side, not like terms, right? So I'm just going to write them all the way out. So I have x log 15 minus x log 5 equals, on the other side, all I have left is 2 log 5. Now, just like that last one that did have the 2 terms with the x's, here's why I wanted to put them on the same side. Because now what am I going to do with the x? Take it out. So I'm going to take out the x, put in parentheses, what's left? So if I take the x out here, I'm left with log 15. Minus, if I take the x out here, I have log 5 equals 2 log 5. Now I can get the x by itself by dividing by this whole thing. So I'm dividing by log 15 minus log 5. Now, this is a little tricky putting it in your calculator. So I'm dividing by log 15 minus log 5. Here's why. When you're doing this, putting this in your calculator, what does it give you as soon as you hit the word log? It gives you an open parentheses. So just make sure when it gives you that open parentheses here that you close it after the 5. Now, when you're doing the denominator, I want to say that all of this is in the same denominator. So you're actually going to put an open parenthesis here. Then remember what it gives you after you type in log. It gives you an open, so you'll have to close. When I type in this log, it's going to give me an open, so I'm going to have to close. But I haven't closed this one yet. So you're actually going to put 2 closed parentheses there at the end. So let's see, up top I have 2 log 5 close divided by, I'm going to open up a parenthesis, log 15, close that one, minus log 5, close, and then another close. And it gives me 2.92994, which just means I don't need to round up the 9s. All right, so that is the exponential equations. Okay, so there's 2 methods. Either you're going to be able to change the base of both sides of your equation to be the same base, and then you'll just make your exponents equal to each other. If that's not a possibility, then you'll log both sides to get the x out of the exponent. All right, now let's do some log equations. Okay, we've actually already done some that are we kind of led into this when we were doing our log section. So if we have log base 6 of x equals 2. Right? Remember that what we're going to want to do, if we can, is turn this into an exponential equation. And remember, we went back and forth between logs exponents a couple of sections ago. Remember the motion that we took, the rotation? This is the base of the log. What's also the base of the exponent, right? So this is going to be my base. You raise it to this power. And then it's equal to what? That x. That's what's in that position. So now that I've changed it to an exponential equation, the x is isolated, right? It's all by itself. I just need to realize what 6 squared is, which is 36. So if your equation only has one log in it, turn it into an exponential equation by using what we did in that log section. What is the base of your log if you don't see it? 10. Good. So if I'm going to turn this one into an exponential equation, I do want to know what the base is. Since I don't see it, it is a 10. Which means now I can turn it into an exponential equation. So I have 2 to the negative 1 power is going to be equal to my x. And then you can just type that in your calculator. 10 to the negative 1 gives me 0.1. Now, in my last class, we had a support section afterwards, and people were doing some of their homework, and that was a 5 right there. So I have 10 to the negative 5 equals x. But when you typed it in his calculator, it gave me this. Now, is that a mode thing? You know, I don't know if it'll ever, I don't think you can ever make it not do that past a certain number of zeros. So what does this mean? This means this right here, if I wanted to be able to do it in my calculator, I would need to make this exponent positive. How do you make it positive? You flip that base, so that would be 1 over 10 to the 5th equals x. Now I can put 10 to the 5th in my calculator. And if I do that, 10 to the 5th gives me 1 over 100,000. So just watch out for that on that problem. If you get an answer like this in your, this number is too high, it's going to give you that funky answer. So just change your exponent to positive by putting it in the denominator. All right, what about this one? Log base of 5 of 4x minus 4 equals 4. So I only have one log, so I'm going to turn it into an exponential equation. So 5 to the 4th power is going to be equal to, what's in this position? So 4x minus 4. So I'm isolating this x. I need to figure out what 5 to the 4th is. If you punch that in your calculator, 5 times 5 times 5 times 5, or 5 to the 4th power, it gives you 625 equals 4x minus 4. And then just use your equation solving skills to get that x by itself. So add the 4 to both sides. So now you've got 629 equals 4x and divided by 4. So x equals, then you can just type that in your calculator. It may actually even take that. Okay, if you have typed it, I can't remember if it takes that in fraction form or not. It doesn't specify in the instructions like it does sometimes, but if it doesn't, then you just type it in your calculator, 157.25. So that's what you do if there's one log. What if there's more than one log? All right, remember that handout that I sent with the logarithm rules and how to simplify them and rewrite them? Like you can rewrite the sum of logs and turn it into one log where they're multiplied. Or you can rewrite the difference of two logs as a quotient, right? So let's look at one that has multiple logs. So if I've got two logs that have the same base on the same side, I want to simplify them by using those log rules. So this one, since it's the sum of two logs, I'm going to rewrite this as one logarithm and turn it into the product or multiplication. So it's going to be log x times x plus 48 equals 2. So what that did is it turned the two logs on the same side into one log. So now it's like the ones I've been working. And now, since there's just one log, I can turn it into an exponential equation. I don't see the base, which means it's 10. So now I have 10 squared equals x times x plus 48. So let's see, 10 squared is 100 equals, distribute this x. So now I have x squared plus 48x. What kind of equation do I have now? That's right, quadratic, which means I can go to my quad program, right? I can always use quad program to solve this, but before I do that, you need to make sure, so your A, B, and C have the right signs, that this 100 comes over here. So I'm going to subtract 100 from both sides. So now I have 0 equals x squared plus 48x minus 100. So if I can either factor that or put it in the quad program. So if you put it in quad, what does it give you? It gives you two answers, right? Which is what? 2 and negative 50. Here's the thing. Remember, what are you solving for? X. So this is where your answers would be. A 2 is fine. But remember when you punched in log of a negative number, what did it tell you in your calculator? That there was a non-real answer. That's not going to work, right? Because it doesn't matter what power you raise a number to, you're not ever going to turn that number negative, right? You can make it, turn it into a decimal, you can turn it into all kinds of things, but you're not going to raise something to a power. So that's why when you get the negative answer, it's not a true solution. All right, let's do one more, and then we'll have to wrap up this section on Wednesday. All right, log base 4 of c plus 16. minus log base 4 of c plus 7 equals log base 4 c. Okay? If I have multiple logs on the same side, if I can simplify that in any way to turn it into just one logarithm, I want to do that first. What is this one going to turn into? Since it's subtraction, the division one. So I'm going to have log base 4 of c plus 16 over c plus 7, right? I just turned it into the quotient, equals log base 4 of c. So now we have something that we haven't seen before. Even though I simplified this side, I actually have logs on both sides, okay? Which actually makes this one easier because, remember, I can do anything I want to an equation as long as I do it to both sides. So why not just divide both sides by log base 4 to cancel them? So if you have logs on the same side, on both sides, just divide them up. And you're left with c plus 16 over c plus 7 equals c. Now, remember way back when, this is what's called, I'm still solving for c. I got c's all over the place. If I can turn this into a proportion, I can make this where I can solve it by cross multiplying. What does cross multiplying say? It says if you multiply one diagonal, it's going to be equal to the multiplication of the other diagonal. What that does, it's going to put all the c's on the same level. There's not going to be fractions with c's and denominators. So let's see if I go this way. C times c plus 7 gives me c squared plus 7c. Right? Do it times both of them. Equals. The other diagonal is c plus 16 times 1, which is just c plus 16. So now where are we at? C squared. So where am I going to go? Quad. Right? So before I go to quad, what do I need to make sure that all my terms are on the same side? So I'll subtract these off of this side and put them over here. So on the right, there's my 0. On the left, c squared. I put the minus c under the 7c so I can put them together. So that leaves me with 6c minus 16. So you can either factor that again or put it in quad. What do you get when you put it in quad? 8 and negative 2. Wait. I was about to say, I think it should be the other way around. 2 and negative 8. Right? Because if you factor it, you'll get c plus 8, c minus 2. So that'll turn into negative 8 and positive 2. Now, this negative 8 I can't use because if I put negative 8 right here, what is it going to turn this into? Negative 1. So that's why the negative 8 doesn't work, just the positive 2.